Okay, so let's start today. Yeah. So now we continue with the computation of the line integral of the derivative and also the derivative over the dt of the sigma function, like plus a period over the sigma function plus a period. So okay, so so okay. Yeah, so this is definitely true for because of pointwise equality, right? So this is true for pointwise equality, and and right. So I think we should get the result by taking the exponential on both sides, right? So okay. I think I have some idea here. So yeah, so we would expect so we would expect after taking the exponentials we get the equality, right? So why don't we just take the exponentials? Oh shoot. So let's take the exponential first, and then let's use some tricks. Sigma of zeta plus omega 1 d zeta, which is equal to the okay, so which is equal to the exponential of the line integral over gamma sigma prime zeta. So I think in order to derive exactly this relation, right? So I have to sort of okay, so let me do that. So because I'm thinking of like in order for this function to be well defined, for the antiderivative of this function to be well defined, we need some simply connectedness of the domain, such that such that such that the antiderivative is actually path independent. Okay, so here what we have, but here so here I'm worried about because this eta 1z basically is being derived from just integrating over the eta 1, right? But in this case, this eta 1 is actually a non-constant function. So if we just ignore this function, so this function, it may have some singularity, right? But this function eta 1 is just eta 1, right? So there's no singularity for this one. So on whatever the domain, like the C, the domain, this function has no holes, right? So basically, so the antiderivative of this function is well defined. So d zeta plus the integral of the gamma eta 1 d zeta okay, so so what do I get? So okay, so the integral, so okay, so for any z, okay, okay, so let me see this. So shoot, I think I need an eraser here. So so let shoot, let z be any okay, so let z be any c minus the set of the lattice point containing 0. Okay, so and that so gamma, let's say from 0 to 1 to c also minus the lattice point. Maybe let me be consistent with the notation that I used before. So avoiding the lattice point, okay, including 0. Yeah. So this wedge is the lattice point union 0. So this take away the lattice point and the origin. Okay. So so be a C1 path. Such that let's say okay, so it starts as the origin. Wait, I don't think it can start at the origin. Yeah, I don't think it can start at the origin. So let's say that it started 1, and yeah, so this z cannot be equal to 1, right? Because I want to say that it ends at z, right? Yeah. So suppose that z not equal to 1, okay. Yeah, so okay, so now because okay, so by the fundamental theorem of line integral, so this is equal to so this is equal to just e to the sigma prime zeta over sigma zeta integral over the line plus. So now so this one, okay, so this guy is equal to okay, so this one is equal to eta 1 z, okay, so minus the endpoint, which is eta 1, okay. Okay, so but this is by the fundamental theorem of line integral. So wait, wait. I think by the fundamental theorem of line integral applied to this function, right? Yeah, let me check actually. Because I'm thinking of like so for the fundamental theorem of line integral, if it's being defined, so because for fundamental theorem of line integral basically says that if you have a, like, say, so this is like a one form, right? So if you have like a C1 function such that the exterior derivative of the C1 function is equal to the C1 form, it's equal to this one form, and then this line integral is actually equal to the gamma at the gamma evaluating so is equal to the C1 function evaluated at gamma at the endpoint minus the gamma of the endpoint of gamma minus the starting point of gamma. Okay. So so if we think of like because I'm not sure, because the C1 the C1 function, it may not be defined in the whole plane, right? So here in this case, this C1 function, we do know that there is a so for every similarly connected domain, right? So this is like a normalization function. So we know that there is guaranteed so there is guaranteed a potential function, C1 potential function for this function. So yeah, so I'm not sure whether this C1, this similarly connected domain may influence our choice. But currently I think I'm looking at another trick that I can use here. So basically, let me write it here. So Okay, so now everything is good right now. So these times so here there's no issue here. Okay, so e to the eta 1z times e to the negative eta 1. Okay, so that's just mimic the form here. So so right now what I want to do is that I want to take the derivative of both sides. Yeah, let's see what happened, because I may get some cancellation. Right. Okay, so maybe now I'm having a problem because okay, so let's see. So taking derivative on both sides. So because I'm aiming at because these exponentials, they take derivative, they keep itself and then times the derivative inside, right? And then these exponential structures are all kept when taking the derivative, but okay, I don't think it may work. Okay, so maybe yeah, so these exponentials, they are kept when taking the derivative, and then I can divide by the things. I can divide by the original functions, right? So the exponentials are cancelled out, so I get a relation about the derivative of here, which is equal to the derivative of here, of the exponential here. So we view it as this guy plus eta 1z. Okay, so just combine these two exponentials such that everything. Oh, this is the view being viewed as a constant term. Okay, so never mind. So what derivatives am I going to take actually? I taking derivative with respect to z. I think. Yes, taking derivative with respect to z, but I think that's equivalent of taking the derivative of just these two functions on both sides, right? Okay, so so what do I? So what do you want to show? So okay, so basically, I think what I want to show here is that I want to show so I want to show e to the integral of gamma of sigma prime zeta over sigma of zeta d zeta is exactly equal to sigma z. Okay. Yeah. So to do that, so what I aim here is that uh, okay. So can we define the log function? Yeah, so I want to define the log function. Okay, so okay. So because okay, so show that I think in order to define the log, I think in order to define the log, right? We need the function to be non-zero, right? So there are points for the sigma z. Yeah, so there are many points actually that the sigma z is equal to 0, right? So namely for z equal to 0 and also z equal to the lattice point. So so we want our log function to be I want our log function to be avoiding this point, right? So, okay, so here we have already take this z to be avoiding the lattice and the 0, right? Okay, so therefore the log is being defined, but there is another issue that whether the log function is actually yeah, so the log function may not be on the same, be globally defined, right? So even though for each point there's a log, but the log function may not be globally defined. So what do we need to do? Let me think. So Okay, so show that. Okay, so let's just take any branch. Okay, so okay, so um, okay, so since um, z is not in this lattice point, okay, c take away this lattice point and 0. So sigma z is not equal to 0, right? So okay, so okay, so now that so we define a principal branch. Okay, so I think I'm running time. So so here so here what I'm aiming for is that define a branch of log that okay, so such that and show that, okay, and show that the integral sigma prime zeta over sigma zeta d zeta is equal to the log of sigma z. Okay.